Hi, everyone. Welcome to the lecture 3 of the module 4. This lecture will be about electric potential. Okay, let's also start with what do you see section. Okay, so what you see on the left-hand side is the model of the thunder. Okay, so how the thunder or the current of electric charge can flow from the cloud to the ground. Okay, so this model trying to describe that the cloud, the part of the cloud has positive charge. Okay, so the bottom part of the cloud has positive charge. Meanwhile, uh, some part of the ground has negative charge. So in the concept in this handout, okay, it would be about electric potential. So we're trying to describe this in terms of positive potential. Okay, we try to describe positive charge in terms of positive potential, and we try to describe negative charge in terms of negative potential. So when you have positive and negative potential, what you're gonna have is the potential different. Okay, so it is the same idea as you have the parallel plate, in which in one plate you have positively charged in it, and in another plate you have negatively charged. You have negative charges in it, and there will be electric field that come from positive charge and going into the negative charge. And if I put a positive charge within this electric field, there is going to be the force that is dragging this positive charge down, and there will be some electric current. Okay, but from the perspective of this lecture, we try to say that okay, for the positively charged plate and negatively charged plate will be positive potential, negative potential, and the delta V or the potential difference. Okay, and then another concept that we are talking about, that we are talking in this lecture, is about potential energy in terms of electric charge. Okay, so let's try to see how I would describe the potential energy again. Okay, so you can see that here I try to bring the positive charge to be closer to the positive charge. Okay, so what happens when I try to bring positive charge close to positive charge? Okay, so there always be the repulsion. Okay, that try to repel two charges from each other. Okay, so if I want to pull or to squeeze two positive charges to be closer together, I need to do some work. Okay, and the work that I do to squeeze them together, okay, will be changed into the potential energy of the charge. Okay, so the outline of today's lecture will be about electric potential from point charges, will be about potential energy, and will be the relationship between electric field and electric field potential. Okay, so we we start discuss briefly about electric field from point charge. So for point charge, it can, if you have a point charge, you know that it can generate electric field as a vector quantity, and it can also generate electric potential, but as a scalar quantity. So here you can find out what would be the potential, and at some any other points you can find out the potential at any places. Okay, so that potential is called a scalar field. Okay, then we also consider the potential from system of charge. So when you have when you have a system of positive and negative charges, you'll be able to find the potential at any point. Okay. Then potential energy. Also, we try to consider potential energy between pair of point charges. Okay, so for example, if I got 1 and 2 and they tend to repel each other due to Coulomb force. So the work that I do to, as I mentioned before, the work that I do to squeeze them together will be the potential energy. Then the system with many pairs of point charge. Okay, so it would be in the case that you have you try to create a system of charges, and you need to do some work in order to get a configuration like this, and all the work done to the system in order to get this, it would be the potential energy. And then we discussed about relationship between electric field and potential for case of parallel plates, spherical conductors, and we discussed about the problem of accelerating charged particles by the potential difference using the conservation of energy. Okay, so let's start with definition of electric potential. Okay, so we start with noting that electric potential is a scalar quantity. Okay, so this part of the picture demonstrate how the charge Q will create electric potential at any point R. Okay, so you can stand at this point and try to find electric field at this point, and you can also stand at this point and in order to find electric field at the other point. Okay, so electric potential of a point charge is defined by a constant 1/4 pi epsilon 0, or it is K equals to 9 times 10 to the 9 Newton meter square per Coulomb square. Okay, so it is it would be proportional to Q, inverse proportional to R. In order to get the high potential, you can increase the charge, or you can bring the point of interest to be closer than the charge, and in order to get the higher potential. And for E, like electric field, so we would like to say that electric potential is a scalar quantity. Meanwhile, the electric field is a vector quantity. So that's, you can see that for potential, there is just only positive sign of the potential, negative sign of a potential, and 0. Okay, so if we consider just only 1 point charge, okay, normally positive charge tends to give you positive potential, and negative charge tends to give you negative potential. Okay, for system with many point charges, okay, so we try to calculate this by summing up the potential from all charges. Okay, so if I stand here and I want to find the potential here, okay, we need to bring the potential from Q1, potential from Q2, Q3, Q4, and Q5, along with the distance R1 from Q1, distance R2 from Q2, and to R5 from Q5, in order to find out the potential from all the charges. Okay, so if I'm interested in this point instead, okay, we just need to draw the distance from all the charges also, and use the relationship. It is K times by sigma Qi over Ri. So because it is come from if I do V, or total potential, it will be potential from 1 plus potential from 2 plus potential from 3 until until the potential from the last one, which is 5. Okay. So that's the total potential. Okay. So we need to sum the potential from all charges. Okay, so that's the key. You need to sum the potential from charges, and the plus minus sign of Q is counted. Okay, so that's if some charges, like if I suppose that charge 3 and charge 5 are negative, so you need to put a negative sign at 3 and negative sign at 5. Okay, so let's have a look at the example. Okay, so this example, we are considering the system of 4 charges. Okay, and we want to find the potential at the point P at the center of the square. Okay, so here, it's just like we try to have this charge as number 1, number 2, number 3, and number 4. And what we try to do is we try to find the total potential as potential from 1, potential from 2, potential from 3, potential from 4. Okay, and we bring we bring out the constant from the outside, and for Q1 over R and Q2 over R, let's see, we use the same R for 1, 2, 3, and 4 because we are considering this distance from the center of the square, which is equal for all the charges. Okay, so that we actually have R equals R1 equals R2 equals R3 equals R4 as a spatial condition for these questions. Okay, and then you use the Pythagoras theorem. Okay, and you find that R can be written in terms of D as D over square root 2. Okay, so that's finally I substitute Q1. This is a Q1. Substitute Q2. Substitute Q3 and Q4. Okay, and then we substitute R as in terms of D. Okay, so finally you need to answer in terms of Q and D because the question gives you Q and D. So if they don't give you the number, you need to answer in terms of the variables that the question gives you. Okay, so this is this example. Okay, and we try again in our example class. So next concept will be about electric potential energy. For electric potential energy, okay, let's try to consider the concept of potential again. Okay, so if we have the source Q, the charge Q, and the charge Q acting as a source for electric potential, and we consider the potential as at a point P. Okay, and then we can calculate the potential by this equation, or sometimes you can, for convenience, you can write this down as KQ over R. Okay. Then for potential energy, consider at the same point, you bring the charge Q into the potential. You bring the charge Q and place it on the potential. So if you bring charge Q and place it on the potential, you find that the potential energy contributed by the pair of charge. Okay, it's contributed by the pair of charge. So I say that this is the potential energy of the pair big Q and small q. Okay, can be written in terms of K. So big Q, which is the charge number 1, and small q, which is the charge number 2, divided by R. Okay, and don't forget that the sign for Q and Q are counted. As if you have a Q as a negative charge, you need to put negative charge on. And if you have Q as positive charge, you need to put the positive sign on. Okay, then we now have the definition of the four quantities, okay, in electrostatics, okay. Firstly, in the first lecture, we study about force and about field, force and electric field, so F and E. And in the last week, we study about Gauss's law, so we study more about electric field. Then for today, we start describing the potential and the potential energy. Okay, so we so we now have some kind of connections between these concepts. Okay, so let's talk about F and E. Okay, so start with, if I say that the charge Q can be acting as a source of electric field. Okay, so if I consider this point and I see electric field going outside from positive charge here, electric field going outside from positive charge. Okay, so when consider at the point P, I can always see that the electric field in this direction outside from Q, okay, can be written in this term. Okay, then if I place a charge Q over here, okay, the charge Q will experience the force from electric field. Okay, so if I got electric field over here, the force that the charge Q is experienced is QE. Okay, then so that's now I have some kind of connection between the concept of F and E by this term, F equals QE. Or sometimes I can see that electric field would be the electric force per unit charge. Okay, then for potential and potential energy, with considering the chart big Q as the source for the electric potential as same as the source for the electric field. So if I place a charge Q at a point P of interest, okay, we can say that the charge Q will have the potential energy of QV. Okay, so that now we have the relationship of U equals QV as the connection. Okay, after that, soon we are going to derive, okay, that for the potential energy and for the force, we normally have the relationship between work and the force. Okay, so work done by, so it is the work done by the electric potential, and we know that for the force in the radial direction, okay, or in any direction, in one-dimensional direction, force can be written in terms of du by dx. Okay, so this is the force of this is gonna be the force of the electric field. Okay, and after, if I bring F equals QE, this one F equals QE, and if I bring U equals QV, you should come up with the relationship between E and V, as E, or electric field, can be written in terms of derivative or diff of the potential, okay, by as E equals minus dV by dx. Okay, and we are proving this relationship later. Okay, now from the definition of the electric potential energy, we try to define the electric potential energy from the group of point charges. Okay, so let me remind you a little bit about if I want to find like electric potential here, electric potential from at any point. Okay, at any point within the space. Okay, from four charges. What I do is I find the total potential from all the charges. Okay, so in this case, the total electric potential at this point, okay, it would be V1 plus V2 plus V3 plus V4. And for example, for V1, I consider this distance. For example, I consider V3, I look at this distance, okay? But for potential energy, okay, I need to remind you very hard that this is not the potential energy from just all the charge. So if I write U1 plus U2 plus U3 plus U4, it is wrong. It is wrong, okay? But for potential energy, we need to consider the energy from all pairs of charges, okay? So all pair of charges mean that the potential energy such as U12 cannot be written in terms of just only one charge, but they should be written in terms of two charges, okay? So that's here I need to do U12 in the four charge system, U13, okay? U13 is the potential energy between these guys. So this is U12. And then U14, according to the dashed line, it is the potential energy between 1 and 4. And not only that, we need to bring all pairs, all unique pairs. 2, 3, 2, 4, and 3, 4. Okay, so here it should consist of 6 terms. Okay, so let's have a look at this example. So to find the total electric potential energy for the 3 charge system. Okay, so we start with giving the number for these charges. Okay, so let's say that this is number 1, number 2, and number 3. Okay, so what we do basically is to find the potential energy for all the pairs. So for 1, 2, 2, 3, and 1, 3. Okay, so for 1, 2 that we have a circle, Q1 and Q2. So we just bring 1 nanocoulomb and minus 2 nanocoulomb. Okay, so let's just see that we strictly count the minus sign over here, and also the distance 3 centimeter. We put in the 0.03. Okay, so this is the first term for U12, and then we substitute the U23 and U13, and then we use the constant of 9 times 10 to the 9. Okay, and finally we get the total potential energy of 0. Okay, the next example, okay, we try to find the electric potential energy for the system of 4 charges and aligned in 3D, in 3 dimensions. Okay, so charge of magnitude Q were placed at each corner of a tetrahedral in which all edges were with length D. Find the total electric potential energy. Okay, so a good point, a good trick for this question is the shape of tetrahedral, okay? So they say that all edges, so this is one edge, is with the distance d. Another edge is also with distance d. This also with distance d, and this also with distance d, okay? All edges. So there are 6 edges, and all edges are with distance d. Okay, and all the charges are q. Okay, so if I try to find the potential energy for each pair, just only for one pair, okay, like if I do like u1 2, so this is 1 and 2, and we guess the potential energy of u1 2. Then if I do from U12, we do U13, U14, U23, U24, then U34, okay? We can find that we have U12 equals U13 and equals to the last one, okay? Everyone equals to q square, okay? It becomes q square because all the charges are q and has the same value, and they have the same values, and over d, okay? We all have the d because the distance of all edges are d, the same thing, okay? So that's in order to find the total potential, we just need to bring 6 2 times with kq square over d. Okay, so it's the same as we mentioned in the slides, and then we try to substitute the q values, and we try to substitute the d values, and then we try to substitute the constant. So you can either use epsilon 0 as 8.85 times 10 to the minus 12, or you can use 1 over 4 pi epsilon 0 as 9 times 10 to the 9. Okay, and you should get the final answer for this. Okay, the next application is about to calculate electric potential energy of a hydrogen atom having electron orbiting around the nucleus, which is the proton. So for hydrogen atoms, we get an electron and a proton, okay, which is having a positive and negative charge. So the things that need to remind you is that the negative charge we see for the electron, the minus 1.6 E, let's say. Okay, so that's finally we should come up with a system with negative potential energy. Okay, so if I want to say something about the negative potential energy, we normally see a negative potential energy. Okay, for the system that particle were trying to attract each other. Okay, and then they finally come up with some kind of particles that tends to stay together as a group. Okay, so this is the system with negative potential energy. But for the system with positive potential energy, you normally have the system that charges get repulsed, okay? Yeah, like this. So if we all have positive charges in the system, it will make the potential energy of the system to be positive, and everything just going straight away. Okay, so another example is to calculate total potential energy. In this case, you have the charges Q1, Q2, and Q3. Okay, so just need to create a triangle with the edges of distance R12, R23, and R13, okay, and try to calculate 1, 2, 2, 3, and 1, 3 for all the 3 pairs of charges in the system, and the total energy. We use the sum of total potential energy of all pairs. Okay. Okay, and for Rutherford experiment, for this one, we we come to use the we come to apply the conservation of energy for this system. So an alpha particle of charge 2e move with kinetic energy towards a gold nucleus with fixed position of gold nucleus. So this one is gold. So this one, the big one is gold, and the small one is the alpha particle. Okay, so we shoot alpha particle from somewhere else. The small one, the alpha particle, we shoot into the gold nucleus from somewhere else, and then the repulsion will make the particles somehow stop and then turn around. Okay, so so what we want to see is they calculate the distance between 2 particles. Sorry, the closest distance between 2 particles. The closest distance comes when the alpha particle has been shot, then the repulsion make it goes back. But before it goes back, this is the closest distance, and we call the closest distance as d. Okay, so using the energy conservation using the energy conservation laws. Sorry. Mouse. Okay. The mouse is not working. Okay, here we are. So we consider the situation to be 1 and 2, or I would say it is before and after. Okay. So before, here I assume that the distance r is approaching infinity. Okay, so I propose this situation as number 1, and after I would say that the alpha particle is stopped. Okay, so at distance r equals infinity, I would say that the potential energy is 0. No potential energy, because when the 2 particles are very far away, they cannot feel each other, and the potential energy and the force and everything becomes 0. Okay, and then they have the kinetic energy K. Okay, then for the situation after, okay, here we can say that the potential energy, it could become the K times by the big Q, the big charge, times by the small charge, and divided by the distance d. But as we assume that the particles stop moving, okay, so we're gonna say that the K kinetic energy is 0. Okay, so with these 2 situations, the total energy before equals the total energy after. Okay, we're gonna have that the EK, or kinetic energy, of kinetic energy of the particle at the beginning, okay, will be equals to the potential energy. Will be equals to the potential energy when the particle stopped, okay, at the distance d. Okay, so if I move from this slide to the other, okay, so they try to bring the kinetic energy Ek from the question, and they try to use the potential energy as and use Q1 as the 2 times E and Q2 as a 79 times E, which are the charges of alpha particles and the gold nuclei. And after they try to solve for D, or the closest distance. Okay, so kinetic energy and electric potential energy. Okay, so this one we try to use the relationship between the work energy theorem to to evaluate the relationship between V and E. Okay, so I will start with explaining this one. Okay, so we start with charge Q in an electric field E accelerated by the force F. Okay, because when we have the charge Q, the charge, and within E, there will be force F equals QE acting on the charge. Then this force F, they bring the charge to travel within a distance. Okay, oh sorry, to travel within distance. Okay, let's say this is distance x1, and this is distance x2, and they move by a distance. So that's the work done by the force, which will increase the kinetic energy by work energy theorem, will be found by integrate f dx. Okay, and as f equals QE, we just bring Q as a constant to outside. Then when we consider in terms of potential, okay, so the point 1 should have potential of V1, the point 2 should have potential of V2. So delta U, or the decrease of the potential energy, okay, delta U, or change in potential energy, can be written in terms of potential. Okay, so because U1 is equal to Q V1 and U2 is equal to Q V2, so we bring the charge, which is a constant, outside. So that's we have the definition of delta U. Okay, then from energy conservation, we consider the change of both kinetic and potential energy. Okay, and then we bring them to equal. So after we bring them to equal, sorry, yeah, after we bring them to equal, and we cancel the Q from both sides. Okay, we come up with the formula in the box. Okay, which is the relationship between electric field and the potential. Okay, so we come to consider some special case. The special case of parallel plate. From parallel plates, we can see from the last lecture by Gauss's law that in case of parallel plate, okay, parallel plate is correspond to the constant electric field. So when electric field is constant, we can bring this constant out from integral, and finally we should find that the potential difference, or if we bring V1 minus V2, we have the potential difference of, because if we say that that electric field comes from the one that has more positive to the other side that has a more negative charge. Okay, so V1 here should be larger than the V2. So potential difference would be the V1 minus V2, and is equal to E times D, or E is the electric field, and D is the total distance separating the parallel plates. Or it is the formula that we know as V equals ED. And V now is the potential difference. Okay, so in this case, it is the potential difference between the two plates. If one is 20, one is 15, potential difference is 5. Something that's very straightforward. Okay. Then we come to consider the case of spherical conductor. We look at the potentials outside and the potential inside. For the potential outside, we try to consider a little bit of Gauss law. That's we try to create Gaussian surface outside. Okay, so when we try to use the Gaussian surface outside from Gauss's law, we can find that E times 4 pi r squared, is equals to Q over epsilon 0, and we got E equals Q over 4 pi epsilon 0 r squared. Okay, so from the definition of for the case of outside the spherical conductor, we are using the potential, the same function as the point charge, or kq over r. Okay, the reason that we can use it, because if I try to find the electric field, okay, using the formula that we have derived before, that E is the minus derivative of V over x over the distance. Okay, so I try to diff this guy, and I get this guy that is agree to Gauss law and Coulomb's law. Okay, so that we can conclude that for the potential outside, we have this V. Okay, then for the potential inside, I create Gauss's surface within the conductor, and as there is no charge here, and there will also be no electric field within the conductor. When there is no electric field, we use this relationship and we integrate it. We find that V is a constant. Okay, so that if I consider this graph between V and R, okay, and when R is equal to big R, this is the radius of the sphere. And in case of outside and inside, so for the case of outside, we have proof that the potential energy, the potential is inverse proportional to R. And then for the case of inside, we have proof that the potential V is constant. Okay, the potential V is constant, and the potential at the surface should be equal to the potential outside, but right at the surface. So that the potential should have the function like this. So V in, so V surface equals to V in, and equals to the constant of k q over big R. Okay, and when the potential inside is constant, it would just be equals to kq over the big R. This is for the spherical conductor. Okay, so accelerating the charge by the potential difference. Okay, so let us consider the conservation of energy. Okay, so I'm not pretty sure what should V1 and V2 will be. Okay, but we know that from the conservation of energy, So the situation before O1 is Q at is at the positive electron, and is not moving anywhere yet. And for number 2, it is Q that has been moved to the other side of the electrode. Okay, so Q1 plus 0 is Q1 plus 0. It is the condition before. Okay, so 0 here, that is it meaning that the particle not moving. Okay, not moving, or the kinetic energy is 0. Okay, and then here it means that the particle started to move. Okay, so then we can then write down QV1 and QV2 together, and they're gonna make the potential different V. Okay, so that now we can write this down in terms of potential different V and the speed small v, so that we can use this volt to accelerate electron or whatever particles to move with a particular speed. Okay, and you can also try to derive the same relationship using Newton's law. So we have the relationship between E, V, and D. Between E, V, and D, and we have F equals QE. So that you can find the acceleration in terms of V and M. Okay. So that acceleration is F over M. So F equals MA, and F equals QE, and E equals V over D. So this is what you get. And then you bring this acceleration. You bring this acceleration into the equation of motion for constant acceleration. So if I put u equal to 0 over here, you're also gonna get this relation that can be used to accelerate an electron or whatever particles by the potential difference. The electron volt unit, okay, the electron volt unit, it has an easy definition, okay, as I'm going to tell you. So electron volt is actually the energy from which we use to accelerate an electron with 1 volt. Okay, how many energy would be? So it is going to be W equals QV stuff. Okay, so Q is electron, and V is 1 volt. Okay, pretty easy. So that we should have one volt, and then times by 1.6 times 10 to the minus 19. And so that 1 electron volt is 1.6 times 10 to the minus 19 joule. Okay. Then consider this example where we try to accelerate. Oh, sorry. Consider this example where we try to accelerate the electron using potential difference of 15. Okay, so we use this equation again, and of course we use 15 volt as the V. Okay. Then you can substitute the charge of electron. Then you can substitute the mass of the electron from Google or whatever. And then you'll be able to find the speed of the electron that has been accelerated by this. Okay, so let's see another example. two horizontal plates of X and Y are 0.75 centimeter apart. Okay, so let's try to read and interpret the example together. So we have the parallel plate. Okay, so when there is a parallel plate, there should be the separation distance d, and we found that 0.75 apart, okay, is the separation distance d. A positive charged particle of mass, okay, we have mass m, is situated in vacuum between the plates. Situated in vacuum, that means this guy is floating and is in equilibrium. Okay, so normally there would be mg. Okay, if you take into account of the mass. Okay, but if there is only mg, the particle will just fall down. So that should be some kind of force that is acting on. Okay, so F. Okay, so let's start with the, so let's continue with the question. They say potential difference between the plates 630 volt. Okay, so that's I would do that. The voltage here is 630 volt. Then if we back to consider the floating force, the force that can bring the charge up. Okay, if the charge has the charge of Q, and it is a positive charge, okay, and if the charge is pointing up, okay, there should be an electric field E that is pointing up too and is saving the charge from falling down. Then when look at this system again, we found that, okay, the value V is known, okay, and E should be equals to V over D. So in this case, we know D and know V. So that no problem if you want to know about the magnitude of the electric field. And to calculate the charge on the particle, okay. So what we do is we firstly consider the equilibrium first, mg and F. Okay, so F is equals to QE because we have the charge Q and we have the electric field E. Okay, and and the plate X must be negative charge and the plate Y must be positive charge in order to direct the direction of the electric field. And then F equals QE and E is equals Q over D. Okay, so that now we can write the equations in terms of variable that we know already. We know M, this is M. We know G, 9.8. We know D, this is D. And then we know V, this is V. So we'll be able to calculate the charge. Okay, then the last example, okay. Two parallel charge square plates separated by distance D are connected to source with potential difference. And the length of each side is A. Calculate the magnitude of the charge on each plate. Okay. So what we want to know is if this plate has a charge of plus Q and minus Q. Okay. We want to know what Q it is. Okay, so if you have the side of small a, the area of big A for each plate is A squared. So no problem with the area. Okay. Then actually what has been given, okay, is D or separation distance, and voltage V. So the first relationship that we need to think about is E equals V over D. And for E, we can write this, we can write down in this term, okay, that it is the term that we have derived for the case of parallel plates in the lecture of Gauss's law. That E is in terms of epsilon zero and is in terms of the charge density or the charge per unit area. Okay, so that now we can write down sigma in terms of charge per unit area, or Q over A, and A is the known values and V is known value, D is known value, epsilon we already know it, so we can crack it to find the Q or to find the amount of charge within the particle very easily. Okay. Okay, so thank you for coming today.